Assalamualaikum and hi everyone. My name is Nur Izzatul Afrina binti Zainuddin. In this video, my friends and I are excited to present you the world of external memory, focusing specifically on your physical characteristic. We will cover the magnetic disks, magnetic tapes, and also optical storage such as CDs and also DVDs. Okay, let's start with magnetic disks, which are prevalent in many of our computers and also servers. So first, for form factor, magnetic disks typically come in two sizes, which is 2.5 and 3.5 inch. Next, for shape, they are enclosed in a rectangular case. And for the material inside, you see or you will find an aluminum or glass platters coated with a magnetic layers and a stainless steel spindle. Next, for the component, key component includes the petals, spindle, read write head, actuator arm, and also the protective enclosure. As for the rotation speed of magnetic disks, this disc spin at speed ranging from 5,400 to 15,000 RPM. And also for the interfaces, they connect to system using interfaces such as SATA, SATA, SAS, and also the older PATA. Okay, next, let's move on to optical storage, which specifically CDs and also DVDs, which have been popular for media and data storage. So firstly, for form factor, both CDs and DVDs have a standard diameter of 120 mm and also 1.2 millimeter thick. As for the shape, they are circular with a center hole. For the material itself, the structure includes a polycarbonate substrate, which is an aluminum reflective layer for CDs, or gold or silicate for DVDs, along with the protective and label coating. As per component, these discs are made up of the substrate reflective layer, protective coating, and also label layer. For the interfaces, they are reached by the optical drives that are typically connected via SATA or USB. Lastly, we have magnetic tape, which are often used for backup and archival storage. For form factor, magnetic tapes come in the form of cassette or cartridges. For the shape, these tapes are housed in a rectangular or square enclosures. And for the material, they are consist of a polyester-based film coated with a magnetic layer. And for the component, the construction includes the base film, magnetic coating, optical back coating, and also a protective coating, rails, and the outer housing. For the interfaces, the interface used is specific to the tape format such as DAT or LTO.
Hi, I'm Beatrice Anna Anthony from Group 7, and I would like to present about hard disk drive. The following picture is what typical hard disk drive looks like. Hard disk drive is also known as a traditional hard disk. It is a sealed aluminum box with a controller electronics on the other side. The electronics control the read or write mechanism and the motor that spins the platters. All the electronics contained on the small part. So to know how hard disks function, we need to take a look inside the hard disk. There are several components inside the hard disk, and we will be focusing on four major components, which are disk, spindle, read or write head, and actuator. The first component of hard disk is platters. Platters are circular, rigid disks coated with magnetic material that store magnetized data. The capacity of the hard disk depends on three things. The first one is the number of platters. More platters inside the hard disk can increase the capacity of the hard disk. The second one is the size of the platter. The bigger the size of the platter, more data can be stored inside the hard disk. The third one is areal density. So what is areal density? It is the amount of data that can be stored per square inch on the platter surface. Higher areal density can store data in a smaller physical space, meaning that even if the size of the platter is small, but it has a high areal density, it can store more data. Lastly, platters is built with a good tolerance and arm mirror smooth. The second component of hard disk is spindle motor. Spindle motor is what causes platter to rotate. The quality of the motor determines the capacity and the speed of hard disk drive. It is built right into a spindle, or it mounted directly below it and spins several platters at a constant rate from 3,600 until 7,200 RPM. So the third component of hard disk is actuator arm. So what is actuator arm? It moves the read or write head around the platters from the upper left corner. So the older hard drives use stepper motor actuator that moves the head based on the motor reacting to stepper pulses. Each pulse moves the actuator over platters in predefined step. We don't use stepper motor actuator anymore because it is prone to alignment problem and it is highly sensitive to heat. So the modern hard drives that we use right now is voice coil actuator. The control movement of the coil towards or away from a permanent magnet based on the amount of current flowing through. This guidance system is called servo. So have you ever wondered how you read or write the data to the platter? So to read and write data to the platter, we use the read or write head that fly above the spinning platter. So it transforms the platter's magnetic field into electrical current to read and the other way to write to the platter. The air pressure created inside the hard disk will leave the heads. If it hit the platter, it can cause a failure. Also, it has a small space between the head and the platter that even if there is dust inside the hard disk, it can stop the spinning of the platter. So just now we have looked into what's inside the hard disk, and now we will look what's beneath the board. So beneath the board there's this one breather hole that it is a connection for the motor that spin the platters, and also it acts as a highly filtered vent hole that let the air pressure inside and outside the hard disk to equalize. Lastly, the breather hole is what causes the read or write head floats above the platter on a cushion of air.
Now, we will explore how data is written to and read from hard disk drive or HDD. Let's look at the write mechanism first. Writing data involves three main steps. In the first step, a current is passed through the coil of the write head. After that, this current generates a magnetic field. Lastly, the magnetic field induces a pattern on the magnetic surface of the platter, representing binary data 1 and 0. Let's move on to read mechanism. There are two types, traditional and contemporary. Let's look at the first one, traditional. In traditional read mechanism, the spinning platter's magnetic fields move relative to the read or write head. This movement induces a current in the read or write head's coil. The induced current is interpreted as binary data. For the next one, contemporary read mechanism. Modern hard disk drive (HDD) use separate heads for reading and writing. There is magnetoresistive MR sensor, where the MR sensor's electrical resistance change based on the magnetic field's direction. The MR sensor has high frequency, enable faster and more accurate data reading. This technology allows greater storage density and faster data access. This is the diagram of inductive write MR read. Now, let's learn this data organization. In this data organization, data is stored in concentric rings called tracks, divided into sectors. Gaps separate tracks. Reducing gaps increases storage capacity. Constant number of bits per track with adjustable packing density for efficiency. This spin at a constant speed, ensuring uniform data access. Lastly, tracks are divided into sectors and block can consist of multiple sectors for efficient data management. This organization ensures efficient disk space use, optimized data, and flexible storage allocation. The next part is this data layout. From the pictures, yellow is usually the typical track, while blue is usually the typical sector. In the data layout, data is stored in concentric tracks divided into pie-shaped sectors. Sectors have a fixed number of bytes, such as 256 or 512. Sectors are grouped into clusters by the drive or operating system OS. There are two types of formatting process, low-level formatting and high-level formatting. In low-level formatting, it establishes track and sectors on the platter. It defines sector boundaries for data storage. In high-level formatting, it writes file storage structures such as file allocation table into the sectors. It also prepares the drive for the file storage and organization. Now, let's learn this velocity. For the first one, bit speed variation, bits near the disk center pass a fixed point slower than those on the outer edge. The next one, space and density issues. Outer tracks have wasted space and lower data density. Next, zones for increased capacity. Using zones with fixed bits per track can increase capacity. It requires more complex security to manage. Lastly, constant angular velocity, CAV. This rotates at a constant speed, creating pie-shaped sectors and concentric tracks. Each track and sector is individually addressable. The head moves to a track and waits for the sector to pass. This is the disk layout method diagram. For the first one, which is constant angular velocity, it shows concentric tracks divided into equal-sized pie-shaped sectors. The second one, multiple zone recording. It shows the disk divided into several zones, each containing multiple tracks.
Hi everyone, my name is Alarsina. In this part, we will take a closer look at RAID. So what is RAID? RAID is a technique that represents redundant arrays of inexpensive disks. Sometimes the inexpensive is replaced with independent. The fundamental principle is using multiple hard disk drives in an array that behaves, in most respects, like a single large fast one. There are 7 levels of RAID, which is called RAID 0 to RAID 6. It consists of 3 general RAID concepts that comprise mirroring, striping, and parity. Next, I will briefly explain those 3 general RAID concepts. Firstly, mirroring. In a RAID system using mirroring, all data is written simultaneously to 2 hard disks. The idea is 100% data redundancy provides full protection against the failure of either of the disks containing the duplicated data. The setups always require an even number of drives for obvious reasons. Not to forget, mirroring is used in RAID 1. This diagram shows the RAID system using mirroring. Moving on to the next one, which is known as striping. It is a technique where data will be split between more than one disk. Striping can be done at the byte level or in blocks. Byte level striping means that the file is broken into bite-sized pieces. The first byte of the file is sent to the first drive, then the second to the second drive, and so on. Meanwhile, block level striping means that each file is split into blocks of a certain size, and those are distributed to the various drives. The size of the blocks used is also called the stripe size or block size, and can be selected from a variety of choices when the array is set up. The way striping is set up varies greatly from level to level, such as RAID 0 uses block level striping without parity, RAID 3 and RAID 7 use byte level striping with parity, and lastly, RAID 4, RAID 5, and RAID 6 use block level striping with parity. This diagram shows the RAID striping configuration. One controller splits files into blocks or bytes and distributes them across several hard disks. The block size determines how many pieces files will be split into. For example, the first block of file 1 is sent to disk 1 and so on. When all 4 disks have one block of file 1, the fifth block goes back to disk 1 and continues until the file is completed. And the third one is parity, which is also called checksum. It is described as a calculated value which is used to mathematically rebuild the data. It is very similar in concept to parity RAM. Parity protection is used with striping, and the end pieces of data are typically the blocks or bytes distributed across the drives in the array. The parity information can either be stored on a separate, dedicated drive, or be mixed with the data across all the drives in the array. Parity is used in RAID 3 to RAID 7, and RAID 5 is the most popular one. So these are the advantages and disadvantages of RAID. Talking about the advantages, RAID probably has higher data security because through the use of redundancy, most RAID levels provide protection for the data stored on the array. Next, fault tolerance. RAID implementations that include redundancy provide a much more reliable overall storage subsystem that can be achieved by a single disk. Thirdly, improve availability by providing fault tolerance and by providing special features that allow for recovery from hardware faults without disruption. And lastly, improve performance by allowing the controller to exploit the capabilities of multiple hard disks to get around performance-limiting mechanical issues on individual hard disks. Then the disadvantages of the RAID is the cost. Implementing a RAID system can impact budgets, particularly in high-level RAID configuration. Moreover, it requires rigorous monitoring and an advanced level of maintenance. Other than that, the complexity. The configuration and management can become more challenging. And lastly, potential slowdown. Certain RAID configurations, like RAID 1 and RAID 5, can lead to slower write performance due to the time it takes to write data from multiple locations.
How many levels of RAID? There are 7 levels of RAID consist of level 0, level 1, level 2, level 3, level 4, level 5, and level 6. The first level is write level 0. The common name used is write 0, and it is used striping technique without parity. Write level 0 has no redundancy because write 0 doesn't back up your data, so if one disk fails, all data is lost. It splits files into chunks and distributes these chunks across multiple disks. This setup in write level 0 boosts speed because multiple disks read and write data simultaneously. And write level 0 also cost effective. Write 0 offers great performance without the added cost of extra disks for redundancy. For write level 2, the common name used is write 2. The technique used is bit level striping with Hamming code. This system splits data into bits and distributes them across several data disks and redundancy disks. It uses Hamming codes, a type of error-corrected code, to create redundant bits. These codes are calculated and stored with the data on special ECC disks. When data is read, the ECC codes are also read to check for errors. If a single bit error is detected, it can be immediately corrected. So, this is summary for write level 2. These are synchronized, very small strips, often single byte or word, error correction calculated across corresponding bits on disk, Multiple priority disks store having code error correction in corresponding position, lots of redundancy. It is expensive and not used. Next, for write level 3, the common name also write tree. The technique used is byte level stripping with dedicated parity. In write tree, data is divided into bytes and spread across multiple disks. Parity information used for error checking is stored on a separate parity disk. If any single disk fails, the system can still function without losing data, as the parity disk prevents a single point of failure. This write level 3 is similar to write 2, only one redundant disk no matter how large the array. Simple parity bit for each set of corresponding bits. Data on failed drive can be reconstructed from surviving data and parity info. Very high transfer rates. For write level 4, the technique used is block level stripping with dedicated parity. Write 4 stripes data across multiple disks in blocks, improving performance and providing fault tolerance with a dedicated parity disk. Unlike RAID 3, which stripes data in bytes, write 4 use blocks, enhancing random access performance. However, like write 5, write 4 use a single parity disk, which can become a bottleneck, particularly for random writes. Each disk operates independently, good for high I/O request rate, large stripes, bit by bit parity calculated across stripe on each disk, parity stored on parity disk. Next, write level 5. The common name is also write 5. The technique used for this level is block level striping with distributed parity. Write 5 stripes data and parity information across 3 or more drives. Unlike write 4, it doesn't use a dedicated parity drive. Instead, it distributes parity blocks across all drives, eliminating the bottleneck of a single parity disk. Fault tolerance is maintained by placing parity information on different drives than the data blocks they protect. This write 5 is similarly like write 4. Parity stripe across all disks, round-robin allocation for parity stripe, avoid write 4 bottleneck at parity disk, commonly used in network server. Lastly, write level 6. The common name for this write is write 6. The technique used is block level striping with dual distributed parity. Write 6 stripes data and parity blocks across multiple drives like write 5, but it calculates 2 sets of parity for each data block. This improves fault tolerance, allowing write 6 to handle the failure of any 2 drives, while other write levels typically handle only 1 drive failure. The summary for write level 6 is 2 parity calculation, stored in separate blocks on different disks, user requirement of n disk needs n plus 2, high data availability, 3 disks need to fail for data loss, significant write penalty.